Okay, welcome back. Now I'm going to do a similar example to what I did in the last example with total internal reflection, but the problem is going to be worded a bit differently. The beam of light is going to be coming from the glass. I'm going to enter it into the glass immediately, and then it's going to be going through this prism, right? It's going to be coming out, and then it's going to be going into air. So I'm going to be asking the question, what should the orientation of this glass be so that the beam coming through this, the first glass, going into the next glass, the totally internally reflects from the triangular prism, right? It reflects back, it does not come out. So let's turn off the light so you can see what I mean. Okay, so you can see here, if I have this beam of light like this, see it's going through the rectangular glass, and it's coming out of the triangular prism, you see? But some of it is reflecting downward, but some of it is also coming out from the triangular prism. So now I rotate this so that the beam coming out glides along the surface like this. So now let me draw the original beam. Basically, the triangular prism was there just to afford us a plane like this, right? So the beam of light was coming through the rectangular prism, right? Through the rectangular glass, it entered the triangular prism. So it just entered and it didn't bend, right? It went like this. So its original direction was headed like this. But as it went from glass to air, it bent outward and then it grazed along the surface. So it experienced total internal reflection. So we can model this equation, this original beam, as an equation y equals mx plus b, right? And then write it down as an equation on the xy axis. So let's define this, for example, as the origin. Just make some random point origin like here. So here's my xy axis. So what would be the equation governing the direction of travel of the original beam in the glass plate? We could model that as y equals mx plus b. Well, if we drew the origin right there at the beginning, then the y-intercept would be 0, right? And then it would be y equals mx. And then m would be the slope of the line. So all I would have to find is the angle of this, right? The angle of inclination, and then it would be right here, it's 38 degrees, right? 38 degrees. Right? So the slope is rise over run, which means rise over run. So it would be tangent of 38, right? So if you know the angle of a line, you could take the slope by just calculating the tangent of that angle, right? So m is going to be tangent of 38. So it would be what? That down is 0.8. So the equation of the line is 0.8x. So then this beam of light is coming in a glass medium. So imagine you had this large glass medium. All of this is glass medium. Okay, so then I can ask, what should the orientation of the top portion of that glass medium be? What should the equation of that line be? So that when this beam comes out, it doesn't actually come out of that beam, but it grazes along the surface, okay, of that equation. So what should the equation of that line be? Y equals mx plus b, right? So we can find the equation of that other line. Okay, so then how do we do that? Well, we're going to calculate, the way to do that is to get the normal line right here, right? And then calculate the critical angle it needs to have. Well, we can already calculate the critical angle by just applying the n of r sine theta critical is equal to n index of refraction of air sine of 90, right? So this is going to be sine of 90, right? Right, so then what will that tell us? That will tell us what that angle needs to be, the theta critical, when it comes to the top surface of that glass plate. So then we have here 1.52 sine of theta critical is 1. So we do 1 divided by 1.52 degrees. So if this one here is 41 degrees, any steeper than that, if I orient it any steeper like this, then it's going to be larger than 41, so that means you're going to have total internal reflection. If I go any less steep than that, the beam will come out, you see? So then, if that's 41, how can I find the equation of that line? Okay, so how do we do that? If we knew this angle, we could figure out the angle of inclination of that line, and then we could take the tangent of that angle that will tell us the slope, right? So if this is 41, what is this angle? There's no way to do this besides extending this original beam of light. Imagine this is going straight, right? So if this is 38, that means this is 38. So we have to use that. So then we have to say 38 plus whatever this angle is, plus 90 plus 41 must equal to 180, right? This whole thing must be 180. So quite a bit of geometry in these kinds of problems again. Okay? So I'm going to say 38 plus whatever that angle is, plus 90 plus 41, right? Plus 41 is equal to 180. Well, if you take the 90 over there, it's like saying 38 plus theta plus 41 is equal to 90. So then 38 plus 41 is equal to what? So then that means theta is 11 degrees. So then what would the equation of that line be? Okay, so then remember the slope of the line is tangent of 11 degrees, but since it's negatively sloped, it's going to be tangent of negative 11 degrees, right? The slope is going to be negative. So then it's going to be, this is y equals 0.8x. So the slope is going to be negative tangent of 11x plus b. Okay, so then you're going to have your tangent of 11 negative 0.2x plus b. So now this puts a restriction on what the slope of that line can be. But the line can be up here, the line can be down here. So as long as the slope of the line is like that, it could be here going down, it could be here going down. Any parallel line like that, the beam of light would come out and would basically graze along the surface. So if the problem told us the y-intercept, right, of that line, it could ask us what is the slope of the line and what is the point of intersection of the two lines, the original line and that line, right? So we can find the theoretical point of intersection. So let's say the problem told us what the y-intercept of that line is, right? So it is, in this case, it is 10, 11, 12, 13 centimeters. So 13 centimeters. So the y-intercept is negative 0.2x plus 13 centimeters, right? So then it could ask us, what is the slope of that, the required slope of that line, if you already have this function, right? If you already know that this function is 0.8x. Now, how did we know in our case that it was 0.8? I just took the tangent of 38. But in the problem, it could just give you this function itself. Or it could say the angle is 38. And then you could take the tangent and find out the slope. Right? And then you would find the required slope of this line. And then it would say, what is the point of intersection of the two? Okay, so then we can set the two equal to each other. 0.8x is equal to negative 0.2x plus 13. The 0.2x would come here and we get 1x is 13 and x equals to 13 centimeters. So if the x is 13 centimeters, the y coordinate of the point of intersection would be what? 0.8 times 13. 0.8 times 13, that would be 24 to 10.4 centimeters. So the predicted point of intersection of the two graphs is 10.4 and 13. So let's see if that is correct. Okay, the distance between here and here is measured here. It's 10, 12 and a half, 12.8 centimeters, this one, the experimental. Experimental is 12.8 centimeters, and then the distance from here to here is 9 centimeters. Okay, y experimental. So my results are decent. Again, with using markers and doing this on the board is a bit difficult, but you can see now application of the concept of critical angle, but now the problem is worded so that it's actually a y equals mx plus b type function. A beam of light comes in from a heavier medium. What should the rotation angle of the top edge of that medium should be? Expressed as an equation, so that when the beam of light goes from the glass to the air, it grazes along the surface and does not penetrate into the air. Right? So then the equation, the answer can be written as an equation, y equals negative 0.2x plus 13, and you can find the intersection between the original beam of light and the intersection of the top surface of that heavier medium. Okay? So it's a good example again of testing all the equations of Snell's law, the critical angle, and then applying it with an equation from algebra. Thank you very much.